Hello everybody, this is Dr. Christopher White and welcome back for part 3 of our video dealing with the lab exercise Interpreting Geologic Maps. So now we're going to move on to question 1, part 1. So in this question you can see we have a topographic map and you can see that we have a start location marked in red. So this marks the location at which a bed of rock has outcropped. And the bed of rock of interest has a dip of 15 degrees. And that dip is due west, so 270. So we know that our layer of rock is dipping down towards the left-hand side or western side of our map. When we also look at our map, we can also see that there is a 50-meter spacing between the major contours. So we have all the pieces of information that we need to allow us to predict probable locations where this layer of rock will outcrop on the surface of the Earth. So once again, you can see we have a graph drawn below our topographic map. So this graph is orientated east-west, so it's going left to right on our map. This obviously matches the dip direction of our layer of rock, so this is what we want. You will also see that the starting height is for this location here, which is 2,500 meters and a major contour line spacing of 50 meters. So if we look at the graph below, you will see that it's stepping down along the y-axis in increments of 100 meters. However, there are intermediate lines in between representing 50-meter increments. So on our graph, we've drawn our starting point at 2,500 meters above sea level, which matches the elevation of our known location. We know our layer of rock has a dip of 15 degrees and we know it is dipping to the west. So we know our layer of rock is dipping 15 degrees towards the left hand or western side of our graph and map. So you can see that I have drawn vertical lines coming off this diagonal line here representing our layer of rock, and I have done that at 50-meter increments. So just like in the worked example, what you're going to do is you are going to mark every location where the vertical line here crosses a contour line of the same height. So in the case of this 2,500 meter line, you can see it's coming up like so. And we know that this contour line here is the 2,500 meter contour line. So if we follow it around, it comes really close right there, then it comes around here, and then eventually it crosses the 2,500 meter line right here. So we're going to have to draw another point right there. We're then going to continue tracing the 2,500 meter line. We're going to come around here, then we're going to come back, we're going to keep going, and then we are crossing the line there as well. So we have another point where our 2,500 meter contour is crossing this vertical line. So we're going to make another point there. So remember, you have to make a mark every time your contour line of the same height crosses the matching vertical line. And of course, these are in 50-meter increments. So this one's going to be the 2,450, this one's going to be the 2,400, etc. And so you are going to have a lot of points on this map because this is quite a complicated topographic map. Now, you will notice it's quite obvious that they've actually helped you a little bit because they've shaded this map. You clearly have a valley running through here. You have another valley running through here. Then you have a ridge of high ground running up here, another ridge of high ground running up here, and then you have several smaller valleys there and there located on the north side of this ridge, and then you have some smaller valleys on the southern flank of this valley. Now, this of course means that your area, your location in which your layer of rock could possibly outcrop is going to have to follow this topography. And so this means that there is the possibility that, for argument's sake, let's say that your layer of rock comes round, follows the headland, and then maybe it turns around along this contour point right here. So it comes up, it comes round, then it follows this contour, and then it disappears off to the top of the map. And that's where that particular portion of the line ends. That does not mean that that's the end of the locations where this layer of rock could possibly outcrop. It's then possible that you could have another point over here, and that your imaginary line could actually reappear here and then follow the contours around here, like so. So there is the possibility that the line that you draw as you start to join up these points could possibly go off the edge of the map and then reappear in another location. So don't think that you have to just join all points together with just one line. So don't imagine you have a situation where you're following the topography around here, you come to this point, you start turning around, this is your final point over here, and then you have to draw a line straight over to the next point over here. Don't do that. Follow the topography. So in this case, your line would come round, and then it's going to follow the topography to the north, and then your line is going to restart at another point along the edge of the map, and then it's going to start following the topography over in that area as well. And so once you've done that, you are going to have marked out the probable locations where this layer of rock could outcrop. And that will be the end for part 1, question 1. Okay, so for part 2, we are going to be looking at satellite imagery. So Bathurst Island is the area which is shown in the satellite image. And this is in Nunavut province in Canada. So this is one of these islands to the north of mainland Canada. So it's one of these areas that is obviously very, very cold and quite difficult to get to. So this is an area where satellite analysis is extremely helpful for geologists. So this particular area was deformed during the Inuitian orogeny. And this produced the Inuitian mountains, and the deformation produced as part of that mountain building event is observed in rocks on these islands above 75 degrees latitude. So once you're above that latitude line, you're going to see the rocks on those islands showing signs of deformation related to the Inuitian orogeny. Now, the orogeny itself occurred between the late Devonian and early Carboniferous, and it led to the deformation of a sequence of rocks that date from the early to mid-Paleozoic. So the deformation affected a package of rocks that contained rocks dating from the Cambrian, the Ordovician, the Silurian, and the majority of the Devonian as well, so both early, middle, and late Devonian rocks, which were laid down before deformation began, were affected by the Inuitian orogeny. Now, if I just zoom in over here on the right, you can see that the rocks exposed do have a rather distinctive pattern to them. In fact, if you look over here on the right especially, you can see you have a bit of a sawtooth or zigzag pattern, which is highly reminiscent of one of the block diagrams that we saw earlier. So if I just come up here, it looks a lot like this. There's that sawtooth pattern on the diagram, and you can see the same sawtooth pattern here as well. So straight away, we can see that the rocks have been deformed because we can obviously pick out geologic structures which are related to deformation in our satellite photograph. And we can also begin to already make an assumption that these structures that we're seeing are quite likely to be anticlines and synclines. The reason that I say this is because if this repeating of the same layers of rock was the result of faulting, we wouldn't be getting this zigzag sawtooth pattern. So this is a strong indicator that what we're looking at are anticlines and synclines. So the deformation that we see in the satellite image isn't just limited to Bathurst Island. There are also very good examples of these anticlines and synclines on the nearby Melville Islands, but there are also several other islands located in the area which show similar anticlines and synclines. Now, when they are outcropping on these islands, these anticlines and synclines all show the same approximate orientation, which is a strong indicator they were all formed by the same event. And the fact they are spread out over such a large area, so between several islands, suggests that whatever this event was would have been quite large. So it's very likely that the deformation that we can see in this satellite image is related to a relatively major orogenic event. So when we look at our satellite image, we can quite clearly see that there are some layers of rock that have a very distinct color to them, so they stand out when compared to the surroundings. And some of these rocks are also obviously forming topographic highs, which would suggest they are harder than some of the other layers of rock which are exposed at the surface. So for instance, we can quite clearly see that we have this line of lighter colored rock coming around here, and so that's quite easy to pick out based on the color, but you can also see that it does appear to be forming quite an obvious topographic high, which would suggest it's more resistant to erosion when compared to this layer of rock here. You can also see we have another layer of rock here, and this one has a slightly different color. It's kind of more an orange brown kind of color right here, and this too is forming topographic highs, so it's obviously slightly more resistant to erosion than these rocks here. Now, the rocks that are in these areas here, we can't really identify them, we can't really classify them because they are covered by vegetation, and this vegetation just gives them a kind of green-brown appearance. So even though the rock here and the rock here are probably different layers of rock, we can't be certain because we can't see them, and so the only way to be certain would be to send a geologist to the area to collect samples. So I'm just going to come down to the next figure, and in this figure you are going to see the satellite image that we were looking at a moment ago, but you will see that I have begun to pick out some of these layers of rock based on the colors that can be seen in the satellite image. So if we look over here on the left, you will see that there are 3 layers of rock which I've picked out. So in blue, so these layers here, we have the blue fjord beds, and these are lower Devonian in age. Then in orange, so this color here, we have the Hecla Bay Formation, and this is middle Devonian. And then in green, here, here, and over there, we have the Parry Island Formation, and this is upper Devonian. So the blue rocks, the rocks that I've picked out in blue, should I say, are going to be the oldest, and the green rocks are going to be the youngest. This is going to be important for when you try and work out whether these features are anticlines or synclines. Now, for question 1, I've also picked out an additional formation. So this is the Beverly Inlet Formation, and this has been picked out in pink, and you can see it here, up here, here. So there's a few locations where I've already picked it out for you. Now, the Beverly Inlet Formation is located between the green Parry Island Formation and the orange Hecla Bay Formation. So this green layer here is the Parry Island Formation, and the orange layer here is the Hecla Bay Formation. And so the Beverly Formation will be located between these 2 layers of rock. And I also point out that it has a lighter color than the surrounding lithologies. So this pink layer of rock is probably going to be visible in our satellite image. So when we are looking at our satellite image, here's the Hecla Bay Formation, here is the Parry Island Formation, and so we know that the Beverly Inlet Formation is going to be somewhere in this area here between these 2 layers, and we know it has a very light color. And so when you look at this satellite image for this feature in particular, you can probably pick out that layer of rock quite easily. So once you've picked it out, you are going to color it in using a pink colored pencil. Now remember, we are looking at an area that has been deformed and it's produced anticlines and synclines. This means that we are going to see the same layers of rock repeating at the surface. So the Beverly Inlet Formation isn't just going to appear in one of these anticlines and synclines. There is a very good chance that it's going to appear in more than one. So we have one anticline or syncline here, and then we're going to move on to the next one. So once again, here's the Hecla Bay Formation picked out in orange. Here is the Parry Island Formation picked out in green. And then we know that between those two formations is going to be the Beverly Inlet Formation. And so once again, look for that light colored layer of rock between these two formations. And, you may even be able to pick out other locations where you see the same thing. So for instance, you could say that maybe this sweep of lighter colored rock here is also the Beverly Inlet Formation, because it would be located between the Hecla Bay Formation right here and the Parry Island Formation located right here. Now, to be clear though, not every light colored rock is going to be the Beverly Inlet Formation. So over here, you can pick out light colored rocks as well. However, they are not the Beverly Inlet Formation because we know they are not located between the Hecla Bay Formation and the Parry Island Formation. Okay, so for question 1, you are going to be picking out the areas where the Beverly Inlet Formation is exposed, and you're going to be marking those with a pink colored pencil or pink highlighter. So on to question 2. So for question 2, we are going to be looking at the blue fjord beds, and these are picked out here in this light blue color. So you can see some here, there's some outcrops here, a couple there, and you can see the sweep of an anticline or a syncline here. You can see it comes around, we have them here, we can see we have another feature here as well. So we can see one side of it there and one side of it here. So the blue fjord beds are occurring on the right hand, so eastern side of our satellite image. And we can spot them quite easily because, as you can see, if we look at the original satellite image, this is the blue fjord beds right here. They once again have a much lighter color than the surrounding area, and they are clearly more resistant to erosion because they're forming topographic highs. So you can see them relatively easily in the satellite image. So for question 2, you are going to be doing exactly what you did in question 1, but you're going to be doing it for the blue fjord formation. And so you are going to be picking out the blue fjord beds with a blue colored pencil or a blue highlighter. And so you know the area of interest is over here on the eastern side of our diagram. Okay, so any of these lighter beds over here in the central and western portion, those are not part of the blue fjord beds. So ignore those. Okay, so for question 2, you're going to pick out where the blue fjord beds are going. And then in question 3, you are going to draw the map symbols along the axis of 3 anticlines or synclines. All right, so you're going to look at this map and you're going to say, right, well, I clearly have one feature here because I can see it closing up and coming back round. So I've got one axis here. I've got another feature right here. So I've got another axis coming through here like that. And then maybe you've got this feature here, which is sweeping round. So you know you have another axis coming through here. So the question is going to be, what are they? Are they anticlines or are they synclines? And as we've already touched on, the way to do this is to look at the ages of the rocks. So when we look at our map here, we know that the blue fjord beds, which are picked out in blue, are the oldest, and the Parry Island Formation, picked out in green, are going to be the youngest of the Devonian rocks in the area that have been deformed. So we know that this is going to be the youngest, and these are going to be the oldest. So that should allow you to work out whether you're looking at an anticline or a syncline. And so you're going to mark out the axis for 3 of these features. So if we take this larger feature right here, we know that the axis itself is clearly coming through here, through the point of this folded green layer here. So we're going to come up. The axis is then obviously coming through this region here, because we can see the hinge right there. And then it's going to continue up here through this feature, because once again, we can see another hinge region right here. So our axis is going to come all the way up through here like so. And the final thing you're going to have to do, though, is you're going to have to use the correct map symbol to denote whether it is an anticline or a syncline. So that's going to require you to return to these diagrams right here. And obviously we have the map symbol for an anticline and the map symbol for a syncline. And so you're going to use the correct map symbol to say, right, this feature is an anticline or syncline. And once you've drawn the axial trace showing where the anticline or syncline is going, you're then going to add the arrows coming off that line or going towards that line to tell me whether it's an anticline or a syncline. Okay, so now we are going to be moving on to part 3. So part 3 is going to be dealing with this map right here. So you can see we have a geologic map. You can see it's been overlaid on a topographic map. You can see the contour lines quite clearly. And you can see that we have a situation where we have repeating stratigraphy. So for instance, we can see we have this red colored rock here, there and there and here. We have this dark blue there and there. We have this kind of hot pink there and there. We have this slightly neon green there and there. We have this purple there and there. And we have this peach colored rock here and here. So we have repeating stratigraphy. Straight away, we're going to be thinking, right, this is either due to a fault or a fold. What could it be? Well, straight away, there's no indication of any faults on the map. So this instantly begins to suggest that what we're looking at is either going to be an anticline or a syncline. So, okay. So for part 3, we are going to be drawing a cross section going from A to A prime. And you will see the topographic profile is given directly below the geologic map. Now, in this instance, you will notice that the topographic profile is not orientated parallel to the line of section on the map. This means that you cannot just say, right, that's where the boundary crosses the line of section right here. I'm going to draw a vertical line straight down and I'm going to mark the boundary position right here on the topographic profile. No, you cannot do that. Remember, you can only do that when the line of section and the topographic profile are running parallel to each other. In this instance, they are not. So in this case, you are going to have to use the paper method. So you're going to take a piece of paper, and on that piece of paper, you're going to lie the straight edge along the line of section, and you're going to mark the start point as A and the end point as A prime. And then along this straight edge, you are going to mark off any locations where a contact hits the line of section. So you're going to put a mark here, 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 there, there, etc. all the way along the line of section. And you can then take this piece of paper and you can then put those points onto the topographic profile. So you have the locations for each of the boundaries on the surface correctly marked on your topographic profile. You will then also see that you have several dip and strike symbols. You will notice that because this is real data, the dip angles are not consistent. So for instance, you can see here, we have a dip of 48, a dip of 52, 45, 45, 40. So you can see the dip angle is changing between these locations. Once again, as you did in previous labs, so for instance, you can see here we have a dip of 52, here we have a dip of 45. When you are drawing this boundary between them, you are going to take the average between those two dip values to draw this boundary here. In the case of this pink layer, you will see that there is no dip or strike symbol associated with it, but we can infer the dip and dip direction for this layer of rock by looking at the layers above and below it. So you can see to the west of it, we have this blue layer, and this has a dip of 48 degrees towards the southeast. In the case of this layer, this kind of neon green layer here, you can see you have a dip of 52 degrees, once again towards the southeast. So when you draw this pink layer, this lower boundary, you are going to be drawing at 48 degrees, and this upper boundary is going to be drawn at 52 degrees. All right, no averaging in this case. You're going to say, right, the lower boundary is going to be angled at the same angle as this outcrop here, and the upper boundary is going to be following this layer of rock right here. And so you are going to be drawing your cross section, and as previously touched on, this is probably an anticline or a syncline. And as soon as you draw your cross section, hopefully it should become pretty clear pretty quickly exactly what geologic structure you are dealing with. Now, another thing that you will notice on the map itself is you can see it's a bit faint, but you will see there is a dashed red line coming down like so. This is the axial trace for an anticline or a syncline. And you will notice that I've put 3 white boxes over the top of the anticline or syncline symbol. So you're going to have to work out what kind of structure it is. So for question 1, you are going to be producing your cross section. And then for question 2, once you've completed your cross section, please use the correct map symbols on this figure to mark the axis of any structures, anticlines and synclines. So this is the point. So for question 2, this is when you're going to draw the arrows on the map telling me whether it is an anticline or a syncline. And of course, that is going to be based on your cross section. I would also point out one thing. You can quite clearly see one very large anticline and syncline right here. However, that is not the only one on the map. If you look up towards the northwestern corner, you will actually see there is another feature. So you will be drawing the axial trace for this anticline and syncline, but there is also another smaller anticline and syncline towards the northwest, for which you will also be marking the axial trace of it and providing the arrows telling me whether it is an anticline or a syncline. So then for question 3, we are going to start thinking about possible causes for this deformation. And we're going to do this because this is going to be the kind of thing we're going to be looking at in the next lab exercise. So for question 3, it asks you, based on the presence of the anticline and or syncline, what kind of deformation did the area experience? So was it extended? So was it stretched? Was the area sheared? Or was the area deformed due to compression? So what kind of compression caused the formation of these anticlines and synclines? Extension, so the crust is being stretched. Sheared, so the crust is essentially, for want of a better way of describing it, being smeared as 2 blocks move past each other. Or compressed, which is the result of 2 blocks hitting each other and pushing against each other. So you will have to work out which type of deformation you think it is. Once again, if you are uncertain, you can refer to your physical geology notes. You can refer to the lecture videos for this course, or if you still feel uncertain, you can send me an email and I will try and guide you towards the correct answer. So then for question 4, it says the map area contains lithologies that have a letter code starting with D. So this means that the age of the layers of rock which we can see in our map area is probably Devonian. Now, this means they're Devonian. When did the deformation presented in this figure occur? And how did you come to that decision? So did the deformation that caused these rocks to become folded, did it occur before the Devonian, or did it occur after the Devonian? And then you're going to have to give a simple explanation, 1, 2, maybe 3 lines tops, about how you came to that decision, about how you came to the conclusion about whether the deformation, or which forms the anticline and syncline that you can see in this map, whether it occurred before the Devonian or after the Devonian. All right, and then that's it for part 3. So thank you for watching this video and have a good day.